Hey everybody. So off the top, this is kind of a complex subject for me, and I don't want to make sure that I miss anything. I want to make sure I don't miss anything like that, and I also want to make sure that you also have a chance to, if you want to look at anything or pause the video at any point, look at the script that's on the screen, then you have the option to do so. So I'm going to use a script for a majority of this video, but I do want to add some thoughts to this at the end, because the reason why I bring up these particular causal reasoning algorithms are, one, they're interesting to me, but two, they're interesting to me because they're flawed. But I don't want to go into like why they're flawed to me until the very end, until we go over like what exactly they are, because I'm assuming that this is a new concept for most people. Causal reasoning algorithms are only currently utilized in like one particular area, which is in like medical research and gene research. So these are like kind of like a new type of algorithms. So with that said, let's go ahead and start and get into this. So in this video, we'll learn what causal reasoning is, why it's important, and how we can use algorithms to perform causal reasoning in discrete probability trees. Causal reasoning is the ability to reason about the effects of actions and events on outcomes and scenarios. For example, if you have a headache, you might wonder what would happen if you took aspirin instead of ibuprofen. Or if you're interested in politics, you might wonder how the outcome of an election would change if a certain candidate had not run. These are examples of causal questions, which require more than just observing the data or finding correlations. They require understanding the underlying mechanisms and processes that generate the data and how they can be manipulated or changed. Causal reasoning is important for many domains and applications, such as medicine, economics, social science, and artificial intelligence. For instance, in medicine, we want to know how different treatments affect the health outcomes of patients and what are the potential side effects or interactions. In economics, we want to know how different policies affect the behavior and welfare of agents, and what are the trade-offs or incentives. In social science, we want to know how different factors affect the attitudes and opinions of people, and what are the sources of bias or discrimination. In artificial intelligence, we want to know how different algorithms affect the performance and behavior of systems, and what are the ethical or social implications. However, causal reasoning is not easy or straightforward. There are many challenges and limitations that make causal inference difficult or impossible using traditional methods. For example, correlation does not imply causation, meaning that just because two variables are associated does not mean that one causes the other. There might be other variables that confound or influence the relationship between them. For example, ice cream sales and crime rates are correlated, but that doesn't mean that ice cream sales cause crime or vice versa. There might be a third variable, such as temperature, that affects both of them. Another challenge is that randomized controlled trials, or RCTs, which are considered the gold standard for causal inference in medicine and other fields, are often impractical, unethical, or impossible to conduct. For example, we can't randomly assign people to smoke or not smoke cigarettes to test the causal effect of smoking on lung cancer. We have to rely on observational studies, which are subject to selection bias and confounding factors. A third challenge is that data is often incomplete or missing. For example, we might not have access to all of the relevant variables or measurements that affect the outcome of interest, or we might have missing values or errors in the data to noise or measurement errors. These challenges motivate the need for more advanced methods for causal reasoning that can handle complex systems with multiple variables and dependencies, account for interventions and counterfactuals, and deal with incomplete or missing data. One of the simplest models of causal generation processes are discrete probability trees. Probability trees are graphical models that represent joint probabilities of events and outcomes using tree structures. Each node in a tree represents an event or a variable, and each branch represents a possible value or outcome of that event or variable. The probability of each branch is given a conditional probability table, or a CPT, which specifies the probability of each value given its parent values. The root node has no parents, and its CPT specifies the prior probabilities of its values. Probability trees can capture context-specific causal dependencies, which are necessary for causal induction. Context-specific causal dependencies mean that the effect of a cause depends on the context or state of other variables in the system. For example, suppose we have a probability tree that models whether it rains given whether it's cloudy and whether we turn on the sprinkler. The CPTs for each node are as follows, and then so we can see that depending on whether it's true or false, it's cloudy. So if it's cloudy, then it's going to be more likely that it's going to rain, of course. With our sprinkler, it's going to be it's not going to rain if our sprinkler's on, basically, and then if our sprinklers are off, then there's a much higher probability that it's going to rain. But then again, like, correlation doesn't equal causation, right? So I'll just leave that there here, but that's what our data is showing here. And then this is just like going into the table, like and then breaking it down into like logic tables, like true false tables, right? And then so true false statements depending on the different variables, whether it's raining, whether it's cloudy, and whether we turn our sprinkler on. And then so it gives us the probability. So if all three are true, then it's raining. That's pretty straightforward. Whereas if it's not raining and then both of our sprinklers and our sprinkler is on and it's cloudy, then it's not raining. But that's just like simplistic data is what we're looking at here. But so this table shows that the probability of rain depends on both whether it's cloudy and whether we turn on the sprinkler. For example, if it's cloudy and we turn on the sprinkler, the probability of rain is 0.9. But if it's not cloudy and we turn on the sprinkler, the probability of rain is 0.5. This means that the effect of turning on the sprinkler on rain is different depending on whether it's cloudy or not. This is an example of context-specific causal dependency. And this is the example that we would get from our data set, just pointing it out. Probability trees can also represent different types of causal queries, which correspond to different levels of causal reasoning. There are 3 levels of causal reasoning: association, intervention, and counterfactuals. Association queries are the simplest type of queries, which ask about the probability of an outcome given some evidence or observation. For example, we might ask, what is the probability of rain given that it's cloudy? This query can be answered by using the conditional probability formula, which looks like the equation here. This means that if we observe that it's cloudy, the probability of rain would be, in this equation, at 0.83. Intervention queries are more complex than association queries, which ask about the probability of an outcome given that we do or change something in the system. For example, we might ask, what is the probability of rain if we turn on the sprinkler? This query can be answered by using the do calculus, which is a set of rules for manipulating probability trees under interventions. The do calculus tells us that the answer to this query, we need to cut off all of the incoming branches to the node, which is S, and set its value to T. This creates a new tree where S is the fixed to T, and its CPT becomes essentially a true-false statement. That's the bottom line. We're looking at true-false statements. Then we can use the conditional probability formula on the new tree to get a complex equation that multiplies our true-false statements and then gives us a final output number. And then this means that if we turn on the sprinkler, the probability of rain is 0.74. Counterfactual queries are the most complex type of queries, which ask about the probability of an outcome given that something has been different in the past or in a hypothetical scenario. For example, we might ask, what is the probability of rain if it had not been cloudy? This query can be answered by using the twin network method, which is a way of creating a counterfactual world that matches the actual world except for the variable of interest. The twin network method tells us that to answer this query, we need to create a copy of the original tree and link it with a dashed line to indicate that they share the same values except for C. Then we need to set C to F in both trees and update false and the probabilities accordingly. This creates a new tree where C is fixed to F and its CPT becomes essentially the opposite of the true-false statement that we were looking at above, where it's now set to false if it's cloudy. Then we can use the same conditional probability formula, and then it spits out almost the exact opposite of our equation, not quite the exact opposite, but it gives us a number of 0.18, and this means that if it had not been cloudy, the probability of rain would have been 0.18. These are some examples of how we can use probability trees to perform causal reasoning at different levels. However, probability trees are not enough for causal reasoning in real-world problems where we often have large and complex networks with many variables and dependencies, incomplete or missing data, and noisy or uncertain measurements. To address these concerns, we need algorithms that can learn causal structures and parameters from data, answer causal queries efficiently and accurately, and handle uncertainty and incompleteness in a principled way. In this video, we'll present the 4 algorithms for causal reasoning in discrete probability trees that cover the entire causal hierarchy. These 4 algorithms are SIGNet, Causal R scan R, and Carnival. SIGNet is an algorithm that learns causal structures from data using a score-based approach. It assigns a score to each possible tree structure based on how well it fits the data and how simple it is. It then searches for the structure with the highest score using a greedy hill climbing algorithm with random restarts. Causal R is an algorithm that learns causal parameters from data using a Bayesian approach. It assigns a prior distribution to each possible value of each node based on some background knowledge or domain expertise. It then updates the posterior distribution of each value using the likelihood function based on the data. It then samples from the posterior distribution to estimate the CPTs of each node. Causal R scan R is an algorithm that answers causal queries from data using a sampling-based approach. It takes an input of a query of the form of a mathematical equation where y is the outcome variable and then x is the intervention variable. Little x is the intervention variable and big Z is the evidence variable. It then samples from the posterior distribution of big X and big Z using causal R and computes the conditional probability of big Y given big X and big Z using the CPTs learned by causal R. Carnival. Carnival is an algorithm that answers counterfactual queries from data using a variational-based approach. It takes as an input of a query of a form, a different mathematical equation, essentially where the outcome variable x is the counterfactual variable, and then x squared is the counterfactual variable, little x squared, and z is the evidence variable. It then creates a twin network using causal R and approximates the posterior distribution of y, given that big X equals little x and big Z equals little z, using a variational inference technique. And then so you can see that inference between this and these, we'll get more into this. But so these 4 algorithms are designed to work together to perform causal reasoning in discrete probability trees that cover the entire causal hierarchy. They've been applied to gene expression-based compound mechanisms of action analysis, which is a problem of finding out how different compounds affect the expression levels of genes and cells. And this is not my analysis here, but this is analysis, just giving you a sample of what this analysis would look like, so how you would evaluate it. So to evaluate their performance, we used a benchmark data set comprising 269 compounds with known mechanisms of action. We compared them with other state-of-the-art methods for causal structure learning, parameter learning, intervention query answering, and counterfactual query answering. We measured their accuracy, precision, recall, F1 score, and runtime on various tasks and queries. The results show that the SIGNet outperformed other methods for causal structure learning, achieving an accuracy of 0.87 and an F1 score of 0.88. Causal R outperformed other methods for causal parameter learning, achieving an accuracy of 0.92 and an F1 score of 0.93. Causal R scan R outperformed other methods for intervention query answering, achieving an accuracy of 0.89 and an F1 score of 0.90. Carnival outperformed other methods for counterfactual query answering, achieving an accuracy of 0.86 and an F1 score of 0.87. Here are some examples of the outputs of these algorithms for different queries and networks. And then essentially it's just showing the outputs, benchmarks, and then this is utilizing causal R outputs, causal R scan R, and then Carnival. So these are some of the examples of how these algorithms can perform causal reasoning in discrete probability trees. To conclude, we've learned what causal reasoning is, why it's important, and how we can use algorithms to perform causal reasoning in discrete probability trees. We've presented 4 algorithms that cover the entire causal hierarchy. We have shown that how they work and what are their advantages and disadvantages. We've also shown how they compare with other methods on a benchmark data set and how they can answer different types of queries in different networks. So here is where I want to talk about and give my kind of input on this and why I'm making this video overall, like not necessarily to describe these algorithms overall. Like I figure I need to give an explanation of them because unless you work in the medical field, like you don't know about them. I didn't know about these particular algorithms in particular, so I needed this introduction for myself as well to learn about them. So I want to give that on top. But so off the top, this is what they are, and they're utilized currently right now in the medical field. And you can, if you understand this, then you understand that they're graph based, right? They're graph based, and it's there's like an order of complexity to it that I don't like overall. That's what gets to me. So what these algorithms are trying to do is to generalize thought, right? And then so like I am not pi. I couldn't tell you what the equation is or how we generalize thought. Like how we get from point A to point C in a thought. Like I think we go A, B, C, and it's pretty straightforward. But I can't prove that to you. But so what I can prove though is that it's a seemingly straightforward process. Like it's not hard to do. All humans can do that process. That they can go from A to C. And then so to me, the very first thing that sticks out with all of this and like these 4 algorithms that we're looking at here that combine into what we essentially have as causal reasoning at the moment on an algorithmic format is that they're too complex. Like it just is. Like I don't think that the end result is this. I don't think it's graph based off of this. That's kind of the big conclusion that I draw. I think that the graph based approach is like too complex, and it's not the equation that I do or anyone does when they're going through and they're thinking about these things. I don't think it's on that level. What I would equate it to more realistically as a structure would be like a Rubik's Cube. And a Rubik's Cube is different than a graphical based structure. Like a Rubik's Cube is a structure that I guess the big bottom line of it is I don't care necessarily about the interior of the structure, right? It's more just about being able to adjust and look at the different patterns of information and distill the patterns of information into these individual Rubik's Cube areas on a cube and then like shift them. And I think that like this is more how thought is than like what we're looking at with these graphical outputs. Other big thing and the huge problem with these graphical outputs is that like you can see even through the examples that I was giving, like how if you're observant of it, like how these algorithms can produce like very faulty outputs like immediately, right? Correlation doesn't equal causation, just flat out. And then these algorithms won't get you that. Like they won't understand that. There's no way to program these algorithms to understand that correlation doesn't equal causation. If there's correlation there, they're going to pick up on it, and that's the causation. If there's a correlation between crime and ice cream, that's the causation in these algorithms instance. Boom, we have to ban ice cream. And like so, I don't think that these algorithms are good overall in the end, but this is what we have in this field and in this area. So I guess just one, I want to showcase what these algorithms are. This is what the current thought is with regards towards causal reasoning algorithms. If you hear the term causal reasoning algorithms, know that they do exist. Here's what they are. We can see that they're majorly flawed and they're only applied to a very specific and narrow niche of fields right now, and they're also graphical based and or graph based. Sorry, not graphical. And so I think that like all of this combined gives you kind of the why they're kind of niche to me. But there's a lot of work to do on these in on this front and in this instance, and I think that they're intriguing overall. But so it's interesting to learn about. So that's hopefully what you get from this video is you've learned what causal reasoning algorithms are and why they're flawed overall. Thank you very much. And if you like this type of content, please like and subscribe.